Hello and welcome to part 3 of Dev Maths and Stats Refresher Course, Lecture 9. Now, in the previous video, we generated several standard normal distributions and added them, and we found that that just gives another normal distribution. And the mean was still 0 because expected value of a plus b plus c is equal to expected value of a plus b and so on. And the variance just gets slightly wider because variance is equal to the sum of the other variances because they're independent. But the basic shape is still a normal distribution. So, to conclude from this, these were all normally distributed random variables, standard normal distribution. Sometimes you see it written like this. A squiggle means that this random variable, or these random variables, follow the normal distribution with mean 0 and standard deviation 1. We created a new one, x5, which was equal to the sum from 2 to 4 of xi, in other words, x2 plus x3 plus x4. We found that when we add those together, the resulting random variable is another normal distribution, and this one follows normal distribution with 0 and mean of 0 and a standard deviation of square root of 3. And that comes from this rule, the square root of 3 thing, for independent u and v. So you add up the variances, so the variance is going to be 3, standard deviation must be square root of 3. So the conclusion for that is that the sum of normally distributed random variables is also normally distributed. Next, we're going to create a new variable, as I indicated at the end of the last video, by squaring x1, and also another variable by squaring x2, x3, x4, and adding those. So let's nip back to the spreadsheet and actually do that. So here, I want this to be equal to the square of x1, and this one's going to be equal to x2 squared plus x3 squared plus x4 squared, 2, 3, yes, okay. And then let's just copy those, fill those in. Hopefully you're trying this yourself to see if it works for you and to get a feel for these random variables and distributions. So you can press F9 a few times and you can see the values you're getting. Previously, when I added these together, the new random variable still had mean of 0. Obviously, the mean of these won't be 0 because they're all positive. And you should be able to work out why they're all positive. There are no more negative ones here. So, what can we do with these? Well, it turns out that because of the squaring, and the squaring converting all the negatives to positive, they no longer follow that nice, neat, normal pattern. They follow a different pattern, and the pattern's called the chi-squared pattern, the chi-squared distribution. So, because we're not sure theoretically what the mean should be, what I'll do is I'll take a threshold here, this 1.2 squared, so 1.44. So theoretically, every time this number has got a square, every time this number is above 1.2, then the square should be above 1.44, yeah? That should work. So that's a reasonable number to take as a boundary. For this one, we can do a similar thing. Actually, I can just use this formula here. So that's taking a threshold of this squared plus this squared plus this squared, the same logic. And let's just see if you can theoretically work out how we could predict how many should be above this threshold. And the formula built into Excel for that is chi-dist. So you put in chi-dist of this number, it's going to tell you what percentages are above that number. You also need to put in something called degree of freedom, I'll explain in a minute. You put that as 1. So that's going to tell us about 0.2 or 0.2 or 20% will be above this number. Just need to multiply that by 1,000 because we have 1,000 numbers. There are 1,000 numbers here, and then you can use this here, will still work. because this counts how many are above this. So this is the prediction using theory of chi-squared distribution, and this is the prediction, and it looks on the whole as though it's doing quite a good job. A bit low, it's quite a good job, so it predicts fairly nicely. And now I can see, if I just copy this across here, this won't be quite so good because I have to adjust this formula. Look, it's way out. I've got to adjust this formula to 3, and now it's doing better. Okay, so it's counting correctly how many will be above here. Now I can explain the number I put in here. This has 1 because this chi-squared variable is a result of squaring one normal variable. So there's one normal variable underlying the chi-squared distribution here. Whereas here, this chi-squared distribution is the sum of 3 normal variables. And the parameter is called the number of degrees of freedom. So you've got 3 independently varying random values. That gives you a chi-squared with 3 degrees of freedom. If it's just 1, you have 1 degree of freedom. So you've got the chi-squared distribution. How are the random variables distributed? Well, like this. If we put those on a chart, this is the first one, which I think was x6, wasn't it? So we're just squaring this normal distribution. So you get this quite highly, it's a highly positively skewed. It's no longer symmetrical because everything on this side, all these negatives, get squared to positive. So you have this skewed thing on one side with only one tail. And then the thing about this distribution is the shape changes as you have more degrees of freedom, because here we've got 3 different random variables squared and added together, so that the values can be higher because there's 3 of them, and also that the shape changes slightly. You get more of a dip down here. This peak gradually moves out to the right as you add more degrees of freedom, whereas it starts out quite steep like that. But they're both called chi-squared distributions, and they have different shapes depending on how many degrees of freedom you have or how many underlying normal variables there are. So conclusion 2 is the sum of squared normally distributed random variables. The sum of squared normally distributed random variables has a chi-squared distribution. The degrees of freedom is the number of independent random variables of normal random variables underlying it. And if you add up from 1 to d normal variables and square them, then what you get is a chi-squared variable. It follows a chi-squared variable with d degrees of freedom. And d is this number, how many normals you're summing, independent normals you're summing, the square of. Okay, finally in this demonstration we create yet another variable, and this one's slightly weird, but it kind of makes sense because what we're doing is we've added some random variables. Subtractions does a similar thing. You always get normals. When you square normal variables, also when you multiply them together, you get chi-squared variables. This is what happens when you divide them. So you have a chi-squared variable divided by another chi-squared variable. You get another kind of distribution, but you have to standardize the chi-squareds by the number of degrees of freedom, just to make it fit the distribution exactly and become predictable. So to standardize it, in other words. So how is this distributed? Let's go and see. So what we want to do here, okay, there's the result of the chi-squared one, and the final column is going to be generating a new variable. So here we're going to enter in a formula which is a little bit more complicated. And we'll start with the one with more degrees of freedom. So that's this chi-squared variable divided by 3 because it has 3 degrees of freedom, and then this one is divided by 1, which makes no difference, but I'll put that in there. See, it's quite a large number comes out, and put this down here. We've got 1,000 instances of that. So you can see they're not all large numbers. This is quite a big variation. So this variable, well, what kind of distribution does that follow? Again, they're all positive. It's nothing like a normal variable because they're all positive. It has a different shape as well to the chi-squared variables again. And this one can show theoretically it follows a third type of distribution, which is the F distribution. So an F distribution is the ratio of two different normal distributions. And if I did like I did before, I'd take as a threshold that, and the 1 actually comes from this threshold divided by 3 for the 3 degrees of freedom, divided by this threshold over 1. So it's the same as the random variable. So I want to try and use theory to predict how many are going to be above that. So it's very similar to the one before. It's F dist. That's the number of the threshold. But there's 2 extra inputs, so you have to put both the degrees of freedom. So one was 3, the other was 1, if I remember correctly. Yes, 3 and 1. So and then that gives the proportion. And then I want to multiply that by 1,000. Try and predict how many there are. So I'm predicting there's going to be 608 of these above 1. And there's 590, so it's sort of the right ballpark. Yeah. So it's not a bad prediction. And that gives you the F distribution. You might notice that you tend to get more above the threshold than you did previously. And that's because when you're dividing, every time you divide by a small number, you tend to get very large numbers. If we put this, I think, on a graph, I think I've done that. Okay, so how's this one distributed, this F distribution? Okay, so it's like this. So this is the F distribution, which is the ratio of this one divided by this one. And you can see it's a bit like this figure, but it's much more skewed. It's really extremely skewed. Because just occasionally you get numbers where you're dividing by very small numbers, so you get colossal numbers. This plot, to make this plot look sensible so you can understand it, I got rid of out of 1,000 values, I had to cut about 50 out. And the biggest one was 3.6 million. So the end of this graph would be quite far to the right. So all you really get is this one column and then just a few figures out there. It's crazily positively skewed. So that's the F distribution. So conclusion for number 3 is that the ratio of two chi-square variables has got an F distribution, and divide each one of these by its relative degrees of freedom, and so you have this. So this standardized divided by this standardized gives you an F distribution. So now we've got our 3 basic distributions. The next video can move on to the topic of sampling, and after sampling then we have one more related distribution to that, and then we're ready to start doing our tests. For now, thanks for watching.